In part A of this problem, we need to draw a free body diagram for each of the three masses. So let's start with the first mass. So free body diagram for mass M1, which is hanging on the left side. So this point is mass M1. There is a gravity force which is pulling it downwards, so M1G, and then there is a tension force pulling it upwards. And if the system is moving, it will obviously be moving this way, so that the acceleration is pointing downwards here because mass M1 is bigger. Now let's do the same thing for mass M2. So we have a gravity force pulling it downwards, M2G, then the normal force from the table. So the table is exerting the force on the mass, which is pulling it upwards. Then there is a tension force on this side. This is tension 1. And then there is a tension force on the other side, which we can call tension 2. And then friction force. Kinetic friction force if the system is moving. Now remember that this mass M2 is going this way, so the friction force would be pointing in opposite direction. So this is the friction force. And the system is accelerating this way. Note that here I've written T1, so this means that this tension is the T1 tension. So now M3. So this is mass M3. There is a gravity force pulling it downwards, so M3G, and tension force going upwards. The system is accelerating this way. So this is acceleration A, pointing upwards. So this is the free body diagram for each of the three masses, and that's part A. In part B of this problem, we now need to find the acceleration of the system. We can find the acceleration of the system by using the Newton's second law for each of the free body diagrams. So let's start with the first one. Now, we first need to introduce the positive direction here. So let's say that the downwards direction is the positive direction. So let's write down the Newton's second law for the first mass. The sum of all forces equals m1 times the acceleration. What are the forces? It's the tension 1 plus m1 g equals m1 a. Now we've chosen the downwards direction as positive, so tension 1 is pointing upwards, so it goes with the negative sign. If we get rid of the vector, then m1g is pointing downwards, so it's positive, so m1g, and m1a is also pointing downwards, so m1a. So let's leave it here for now. Now let's look at mass m2. Again, we can write the Newton's second law. Sum of all forces is equal to mass m2 times the acceleration. So in this case, we have force T1, force N, T2, friction force, and M2G equals M2A. So this is the Newton's second law in a vector form, and now we need to look at the horizontal and vertical components. So again, we can look, we need to introduce the positive and negative directions here. So positive direction, if this M1 is pointing downwards as positive, then we should choose this one as positive, because the system is moving this way. So that's why this direction for the horizontal direction is taken as positive. Now let's look at the vertical first. Now remember that the system, this mass M2 only has acceleration in the horizontal direction. So there is no acceleration in the vertical direction, which means that when I write this equation for the vertical component only, on the right hand side I will have 0 because the acceleration in the vertical direction is 0. So in principle we can just ignore the vertical direction. So let's just focus on the horizontal. So for the horizontal, T1 is positive, so it goes with a plus sign. Normal is vertical, we ignore it here. T2 is negative, so it's minus T2, minus force of friction. It's also pointing in this direction. M2G is also a vertical, so we don't include it here. Equals M2A. Now, we are given in the problem the coefficient of kinetic friction. So we can relate the coefficient of friction force to the coefficient of kinetic friction and the normal force. The friction force is equal to normal times the coefficient of kinetic friction, mu k. Now what do we do with the normal force? With the normal force happens to be equal to mg, and it actually follows from the vertical components of this Newton's second law. Remember, we've ignored normal and m2g when we were looking at the horizontal component. If you introduce a vertical direction, for example, the upwards direction as being positive for the vertical component, then the Newton's second law for the vertical component will say that normal minus m2g is equal to m2 times acceleration in the vertical component, which is 0. Which means that normal is equal to m2g. So instead of m, we can just write here m2g mu k. Okay? So now let's look at the third mass. Sum of all forces equals m3a T2 plus m3g equals m3a. Now, remember, we've chosen this downwards direction for M1 as positive. This one is positive, so the positive direction for M3 would be now upwards. Which means that T2 is positive, M3G is negative, and M3A is positive. So now we have 4 equations that we will use to find the acceleration. So we have equation number 1, number 2, number 3, and number 4. So what I would like to do is I would like to express T1 from this equation and plug it in here. Take T2 from this equation and plug it in here. And take the friction force and plug it in for the friction force here. So I have T1, from this equation you can see that T1 is equal to m1g minus m1a. So this is T1. m1g minus m1a. Then comes minus T2. So minus T2, and T2 from here is equal to m3a plus m3g. m3a plus m3g. And now the friction force. So minus the friction force, and we know that the friction force is this. So minus m2 g mu k. And this is equal to m2 a. So now we need to solve for a. So here I have m1g minus m3g minus m2g mu k, and on the other side I have a m1 plus m2 plus m3. So now we can solve for acceleration. So acceleration is equal to, now I'll take this g out, so g, in the numerator I have m1 minus m3 minus m2 mu k, divided by m1 plus m2 plus m3. So now we just need to plug in the numbers. So free fall acceleration is 9.81. M1 is 4 kilograms. M3 is 2 kilograms. M2 is 1 kilogram. Free fall coefficient of friction is 0.35. So M1 is 4 plus 1 plus 2. And if you do the math, you should get 2.31 meter per second squared. And that gives the answer to part B. So in part B of this question, we found the acceleration of the system to be 2.31 meter per second squared. In part C now, we need to find the tension in each cable. So let's start with T1. So from this equation, T1 is equal to M1 G minus A. So this is M1 is 4 kilogram, 9.81 minus 2.31, and we get around 30 newtons for tension 1. Now let's look at tension 2. Tension 2 is equal to M3 A plus G. So M3 is equal to 2 kilograms, acceleration 2.31 plus 9.81, and this gives you 24.2 newtons. And this is the answer to part C of the question. In part D of the question, we need to answer what would happen to the tensions in the cables if the tabletop was smooth. Now, when we say that the tabletop is smooth, we mean that the coefficient of kinetic friction is basically 0. To answer to that question, let's look at the symbolic expression for the acceleration that we found in part B. We said that acceleration is equal to G M1 minus M2 mu K minus M3 M1 plus M2 plus M3. If your acceleration is zero, if your coefficient of kinetic friction is zero, that is, this part is zero, then you can calculate for acceleration to be 2.80 meter per second squared. So the acceleration of the system will obviously increase if the friction is not there. So if the acceleration increases, let's look at tension 1. This will decrease tension 1. As for tension 2, because we have summation here, the tension 2 will increase. So the answer to part D is tension 1 will increase, and tension 1 will decrease and tension 2 will increase because of the increase in the acceleration of the system.